In the following video, the code for implementing circular movements with the robot will be shown, as well as a demonstration with the simulation and with the physical robot. This is the code for implementing circular movements in the robot. So what we will see now are, first of all, the functions that are new. For example, the function cross product. This will be really useful with some operations with points, with x, y, z coordinates, because we need to do the cross product of some of them. So this function just returns the x, y, z coordinates of the cross product of two different vectors. The second function that is new is transpoints, which multiplies a transformation matrix 4x4 with a vector of a point. So this is just the mathematical operations for doing so, and it returns the new point. So now let's go to the function that implements the circular movements. This function is moveC. The arguments that are being passed are, first of all, the value of the joints in the initial position, the position of the tool in the first point of the circle, and in the second point, the time during which the trajectory will be done, the measurements of the robots, and in this vector, the function will store the value of the joints at the final position in the circle. So these are auxiliary variables, and the first step is to obtain the position of the tool in the initial point. With everything that is called serial print, what we are doing is getting the values that are being indicated, so that when we try the monitor series, we can see the results that are being obtained at each point. This helps a lot debugging the code, because we could compare it with a Matlab code that gave the correct results. In this way, it was easier to find the mistakes in the code. Okay, so here there are some more operations that were required to obtain the different parameters that will finally give the circular trajectory. And well, as you can see, we use the functions that are new, for example, cross product here, and transpoints here. And well, at a certain point, one of the parameters could have two different values, that is theta in the final point of the trajectory that could follow this formula or this other. So what we did to check which one of the two is correct is calculate both of them, and now since this is the angle in the last position, we have to check that when computing the position of the tool following this is the function of the trajectory, and when substituting the angle with θ1, what we should obtain is the final point of the circle, which was data given. So with the serial print, we can see in the series monitor if this is the point that we gave the function or not. At first, we assume that theta t1 is the correct one, and we pass this value to theta t. But it can be the case that this is not correct. So we are using this condition. First of all, we are using casts, and we are putting the position of the tool in the final point that was obtained here with an int, because comparing numbers with floating points is not recommendable at all when coding. So we are comparing the position x obtained with the one that we pass to the function, the y, and the z. And we are checking if x position is not equal to the one that we gave, or y position is not equal to the one that we gave, or the z position is not equal to the one that we gave, then this first assumption is not correct, and theta t is actually theta t2 with the second function that was implemented. And from then, the only steps are just putting the parameters for the circular trajectory and evaluating this trajectory at each point in time. We finally obtain the position of the tool in each of the times, and with inverse kinematics we can get the value of the joints at each of these points and pass it to the servos. At the final point, Qt will store the value of the joints in the final position, and thus when using this function, what we will be storing in Qt, in this Qt, will be the position of the joints at the final point, which, as said before, is useful when concatenating functions. So now in the points that were given are 9 in groups of three, so that 3 of them belong to a circle in each of the planes. So these three points belong to a circle in the xy plane. These 3 belong to a circle in the yz, and these 3 belong to a circle in the xz. So now in the setup, we just start by putting all servos at 90 degrees, and now what we are doing is from 90 degrees to the second point, passing through the first point in 2 seconds, and we store the final position in this vector. Now, again with move C, from the final position of the previous function, we go to the point 3 and back to the initial position in 2.5 seconds, and then we wait for 4 seconds. This is for implementing the XY plane, and the same philosophy is followed when performing the movements in the YZ plane and the movements in the XZ plane. What we are going to do now is to see the serial monitor and see what we are getting in it, and afterwards we will see the Matlab code to show how it was debugged, how the code was debugged. Okay, so this is the serial monitor, and well, first of all we have the initial value of the joints, which is 90 for all of them, and now what we can see is all the intermediate values that were being got during the moveC function. So for example, the position of the tool in the initial point, the value of the joints in this initial point, and other variables such as the transformation matrix or the inverse transformation matrix, the points with respect to the new reference frame, the center, the radius, and it is interesting to see here the theta t that had 2 options. And here we see that the final point using the first theta is have these values that coincide with the first point that is, with the final point of the circular movement. So it is the correct value of theta, as you can see here. Okay, so now we will go to the Matlab code that was used to debug this code by comparing it with the serial monitor. The code for the circular movement was actually really difficult to make it correctly. So this Matlab code was used to debug and see at which points the function was not working. So the first step is putting the points that are given to the function and the time. Afterwards, what we have here are all the operations that are being done in the code. And well, now all of them are commented, but when the program was run, here in the screen, in the command window, the values of each one of these functions were obtained, and we could compare it with the ones in the serial monitor and see at what point of the code in Arduino the function was not working as we wanted. And this code was also used to obtain the points that belong to the same circle, which are these lines here. These lines use the equation of the circle with the x and y coordinates because, as you remember, the circles are defined only in the planes xy, yz, or xz. That means that one of the variables, x, y, or z, is never changing, and thus it didn't make sense to implement this with the 3 dimensions. This was just to try some different values of points and implement a perfect circle. The XY circle was not implemented with this, and as you will see, it doesn't describe a circle, but instead 2 arcs that look more like an ellipsis. We will now see the implementation in the simulation. So first we will see a circle in XY, then in YZ, and finally in XZ. But we have to remember that in XY it's not a perfect circle, but instead 2 arcs that may look maybe like an ellipsis. And this is because those points were not chosen using the Matlab function, and therefore they do not describe a perfect circle. So let's start. Now we start with the XY plane, and remember, this is not a perfect circle. Now with the YZ plane, which is a perfect circle. And finally, with the XZ plane, which is too a perfect circle. Now we will go to the physical robot. Okay, we will now see the demonstration in the physical robot. So let's start. First, we have the circle in the XY plane. Well, it's not a circle, it's more of an ellipsis. Now, in the YZ plane, and finally in the XZ plane. So as we can see, it works correctly. In this video, it has been explained the code for implementing circular movements with the robot. It has also been shown a demonstration with the simulation and with the physical robot.